India. But so overall, my 18 years has been into medical devices and specifically in orthopedics. So I have core expertise or interest in, let's say, knees and hips. Knees, in the sense you might have heard about knee replacements. So that's what I design. Knees as an implants and instruments which goes to do the implants, and the trays which houses those implant instruments, and packaging which houses those implants. So it's all related to knees and the hip replacements or hip joint replacements, which nowadays it's very famous, but in general, that's what I have been designing past 18 years. Regarding recent, I mean, my achievements and roles, I have led launch multiple global and local India-specific projects in orthopedics. So I've launched like 3 global products and 2 global products or 2 local products, which is based out of India. We started one first cadaver lab in MS Ramaya. I still remember they started it, and we were the first customer. I was basically a first person to use those cadaver labs, and it was something very truly achievable at that point of time. But now it's more available other than the government institutes. I lead cross-functional teams for new product development, specifically in orthopedics. And again, what cross-functional team means is it's not just the designer who designs the products, right? Everyone knows the designer, right? Who designs the product. But being this a regulated industry, it's not just the designer or design engineer or a researcher who does innovates. It is a quality engineer, where there's a regulatory engineer, right, who needs to understand the regulations around the globe and align our verification and validation strategies so that we can comply with those regulations and launch the product. You may innovate any new product, but until and unless you are able to submit and pass the regulations of a particular country, you can never launch in the end. So never launch the product. So it is one of the core functions of the devices. The fourth core function, manufacturing. Now you can design something, but is it manufacturable? Is it manufacturable in the right way? Again, imagine you implant something inside your body and there is an infection to it. Your whole surgery goes for a toss, your devices goes nowhere, and you are having an infection which causes to patients. So the cross-functional teams are core like product development, regulatory, quality, as well as the operations, or you could say manufacturing. So these are some things which I lead. I also am a DPO or design process owner for design controls. So it's design controls is a part of 13485 requirements, or you can say FDA requirements, where you need to document your design controls so that it has translated from your voice of customer to the design inputs, how you are going to verify your design inputs, and ultimately what is the verification and validation which you've done so that the device is safe and effective, is performing as it is required, and also meets the regulatory standards. So these are general design controls. Again, there are various layers into design controls, like design failure mode effect analysis, where you understand the risk to your design. There is a PFMEA, or product failure mode analysis, or process failure mode analysis. There's a risk assessment in terms of 14971, which is an assessment of a risk based on the patient's harm. So one is top-down approach, one is the bottoms-up approach, but then these are various approaches which are part of a design control. Again, it's a must for any medical devices, be it class 3, class 2, or class 1 devices as well. Again, I provide technical oversight to new product and sustenance projects. And obviously, I'm a proud patent holder, which is a custom instrument which we designed and launched in India. I was basically R&D lead for doing that, and we successfully launched in India, which was a first for Striker. Any questions, any thoughts, you can raise your hands or ask directly, and else we can move to the next slides. Okay, no questions? If you have, you can ask. Right, so you were asking something? Sorry.
No,
Okay.
please continue, sir.
Sure. So just to tell, I mean, what are orthopedic implants, right? So again, my experience, since it's a biomedical, my experience has been in orthopedics. So I'll just focus more on orthopedic side, orthopedic implants. Again, there are maybe few applications in 3D printing in different segments of the devices, but it has most application in terms of orthopedics. So I'll just focus on that, right? So some of the images I kept below, right? The one is you see which is the implants for trauma. The second one is the implants which is for knees. The third image you see is the implants for hips, and the last image is for the spine. Again, different applications, different variety. Again, mostly metallic, ceramic, or plastics, which goes into all of this orthopedic. So most of the time, orthopedic surgeons are also known as carpenter, or some people call them the like beautiful carpentry. But that's how the orthopedics is. Again, there are advancements in orthopedics which we'll go through. But to even summarize, orthopedic implants are medical devices surgically placed inside the body, right? So it's not something like your BP or monitors or ECGs or X-rays which stands outside. These are the devices basically going inside your body, stays in the body, and performs in the body in order to support, repair, or replace bones. Now, support is so when you're walking, it supports your load. It's to repair or replace bonds because certain times your bones gets degenerated because of various deficiencies or even accidents. So it needs to get replaced. Joints, tendons, or ligaments that are damaged due to injury, disease, or structural abnormality. Right? Injury is something which happens when you are traveling or due to accident or when you fall in the bathroom, which are general causes of injury. Disease is something like arthritis or rheumatoid arthritis, or structural abnormality, which is basically your genetic abnormalities, which comes during the birth or comes in later on. Again, the primary use is to restore structural integrity, improve mobility, reduce pain, and enable effective healing of musculoskeletal system. So structural integrity is something which so that you can stand and walk. Improve mobility is provides mobility. It's reducing pain. So I would say the second and third, which is improve mobility and reduce pain, are the most causes of joints which are replaced other than the trauma cases. But improving mobility, you might have seen any old age patients who are not mobile or have been bedridden because their knees hurts or their hips are broken. So it provides mobility, reduces pain because they are not able to mobile because they are under immense pain, which ultimately it happens because of bone-to-bone interaction, it's knees or hips, and effective healing of musculoskeletal system. So this is in general the orthopedic implants definition. But again, there can be varied definition, but ultimately it's to repair or replace certain joints, which ultimately is giving you pain, is to relieve pain and provide mobility. It is nowhere curing the disease because you cannot. These are the disease which you cannot cure. It is to support your mobility and reduce pain. That's how the mobility is restored, but it will not cure your disease inherently because those diseases are because of certain you can say abnormalities or reducing minerals inside your body, and which at the certain ages it is not possible to restore those the minerals in the body. So this is just the terminology. Any questions? Um, you can ask any stupid questions also, no problem with that. It would be good if it's interactive, but again, this is my general knowledge and awareness, which I'm telling you. By the way, I'm not sure if how many of you have attended the surgery, live surgery or cadaver bones, cadaver labs. Maybe I have attended around 50 surgeries. I don't do surgeries, but I have attended surgeries. And it's difficult to do the cadavers. Cadavers are the dead bodies, if some of you might not know. But then those are the noble cause which people donate body. And ultimately, it's the surgeons who practice and develop these products so that it's safe and effective to be used on the live patient. So I've done about 30 to 40 cadavers as well, ultimately to try and develop new products, which can ultimately do the justice to all these things. So technology evaluation in manufacturing of implants. Again, we go from evolution of the implants manufacturing. Everyone knows like traditional machining operations, right? The machining is when you remove the material from the existing bar stock. Forging is something you do either cold forging or hot forging. Mostly it's hot forging, which you do for manufacturing. And then the casting. So these are just the regular manufacturing process, which has been employed into the manufacturing of implant systems also. Again, the material can be different, like cobalt chrome, titanium, or SS as well in certain cases. But these are the conventional manufacturing process which has been employed. Again, these are not conventional, but they are still being employed into the manufacturing of implants. But this has been the forefront since ever, since the starting of the device markets. Then there are other post-processing manufacturing processes also, like HA coating, hydroxyapatite coating, which is done on the implants to provide better fixation, polishing, because certain implants are, mobile, or once you have a mobility, you need to have a polished surface so that there is no scratches and it lasts longer. And third one is the bone cement. So again, bone cement is certain chemical compositions which you implant so that your implant gets fixed inside the bone. So these are the conventional manufacturing, and then you add certain manufacturing processes to enhance this conventional manufacturing process, and so that your devices becomes more effective when implanted into the bone. Now, why I'm discussing this has been conventional and this has been going on rounds, but then there has been a recent, developments in terms of manufacturing process known as a 3D printing, right? Everyone has heard about it. Now, why I'm saying that it's not that, so when you are doing a manufacturing process like machining, forging, casting, these are mass production processes, right? Whereas 3D printing till now, and again, it's still there, it's still a customized level only. We don't generally still have a mass manufacturing of this. Mass manufacturing, when you are manufacturing, let's say, the 2,000, 5,000, 10,000 pieces. It is evolving. I'm not saying that it will not be there. We have started manufacturing these implants in hundreds and thousands, but still the technology advancements to do it such mass manufacturing is still don't exist. But why I'm saying that 3D printing, again, it combines the conventional manufacturing process as well as the manufacturing support manufacturing process like coating, polishing, and to an extent bone cement. Because of the nature of 3D printing, it can produce different shapes. It can provide certain rigidity to the materials, and also it provides coating effect so that we don't require certain cases HA coating, or sometimes polished surfaces also are not required because we don't require mobility that area. And bone cement is something which you don't require because, see, ultimately the bone cement is used to fix an implant inside the bone, right? So there is a cementing effect, so that because the implant is a structural part and bone is you can say porous part, so that it ultimately binds these two. But with 3D printing, you can create such kind of a porous structure so that there is a natural, fitment inside the bone porosity, and it ultimately binds inside the bone, and you don't need a bone cement. So that's why there is a press fit, or you can say cementless applications, which has been very predominant because of the evolvement of this 3D printing technology. There were other technologies which were doing earlier rounds like plasma spray and everything, but still it was a conventional process. This has really up the curve in terms of putting it in one manufacturing process, and you can combine these two conventional as well as the secondary manufacturing process into one. So with the evolvement of 3D printing, it has really evolved overall manufacturing process. But just one thing, it has not been yet able to succeed in terms of business aspects of mass manufacturing with the investment required. So this is the evolution of implants, you can say, from manufacturing process. And that's how this 3D printing technology has come into forefront. Earlier, 3D printing was there, but it was mainly related to plastics. But with metal now, it is really helping evolve into the implants business as well. Any questions, thoughts, comments?
There is a one question. There is a one question from participant.
Yes.
He is Dr. Rameswar Sugandhi. We want to know what special protocols does your team adopt to ensure biocompatibility and safety of custom implants procedure produced using 3D printing technology?
So again, the biocompatibility, right? So
Right.
biocompatibility is not related to the manufacturing process. Biocompatibility is related to two things. One is your base material, which needs to be biocompatible. The other one is your any chemical process, because any chemicals you used or alters the composition of that final product. So if your base material, let's say you're using a titanium in your implants, and the same titanium powder you're using to 3D print the components or the implants, then your biocompatibility is not affected. The second portion, the chemicals used. So chemicals is highly used in machining, forging, or even casting processes. But when 3D printing, you don't use chemicals most of the time. So that's where your biocompatibility remains intact as long as your base material is biocompatible or your powder form is biocompatible, and any chemicals you are using does not alter your composition so that it becomes a non-biocompatible. So this is the basic in terms of biocompatibility. And again, that's why it took a little longer time to evolve this 3D printing into the medical devices. It was there in aerospace earlier, but with 3D printing on metals, it has really helped in improving the biocompatibility. And obviously, sterility is another aspect, which is based on your design and not on just based on material, which is a different case. So biocompatibility remains intact till the point you use the base material, which is biocompatible.
Thank you, sir. I hope participant got their answer.
Okay. Thank you. So again, I'll just look into the surgical technology evaluation or evolution as well, right? Again, manufacturing process is one thing, but then to adopt it into the mainstream, it has to be, see, you can devise an implant, right? You can do various curvatures, but then how do you place it inside the body is also an important aspect, because if surgeon is not able to place it inside the body, there is no use of however you do a 3D printed implants or implants shapes or anything, because surgeon has a very limited time, but limited time window within which he has to do surgery. He has to visibly see where he's placing the implant, whether he is able to implant it in the right orientation and within the specific period of time, right? You cannot do a surgery for 24 hours. You cannot do a surgery for 8 hours or 10 hours because the patients are very old and the blood loss, the more the time you spend, the blood loss goes heavy and the patient's parameters go wild within that time frame. So it's not just the implant, but it's also the technology or surgical technology with which you place the implant is also an important aspect. So I'll just run through the surgical evaluation or surgical technology evaluation which happened and which ultimately helps in 3D printing or custom implants as well. So like conventional surgeries are something which, you place the implants with respect to mechanical instruments like cutting, guiding, even measuring instruments once you have opened your surgeon's patient's incision, right? Now, there was an advancement of surgical navigation, which was around 94, 96 time frame, which was very in thing. Till now, this technology exists and people use it inside the surgery. Obviously, there's an advancement to it, but it was a very good technique which removed certain challenges from a surgeon's perspective, right? What does a surgical navigation do? Imagine earlier we used to travel, right? We used to see the map and then we used to drive, right? We never used to have Google Maps or anything. So that's how, but in while driving through the roads, if the road is closed, then we are nowhere. I mean, then we fumble, okay, where is the alternate road? You have to ask people and then go, right? So same technology, same challenge exists in the surgery. So once you open the wound, what is there inside? It's really a mystery. You can see some things in X-ray, but once you open with the incision, then you will see that, okay, it's really complex inside. So what did surgical navigation is technically a GPS inside the OT with relative to a patient. How we do a GPS in terms of world map, right? So surgical navigation basically tracks you and provides you a guidance of what is your implant placement, what is your implant's orientation, whether the implant's orientation is correct or not, and whether it provides ultimately a measurable outcome, right? Where surgeons till I know, like in the hip surgery, they used to place the head. There is an alignment guide. The alignment and how they used to see, okay, this straight line of the instrument should align with the corner of my room. That's how they used to decide, okay, this is the right angle to it because it's a 3D angle, no one can see. So that's how the surgeon used to do it. Okay, they're placing the cup, whether this alignment, okay, whether it's aligning with the corner line of my room. And that was their measure of alignment is correct or not. This technology provided the insights of whether you are off by 2 degree, 1 degree, 3 degree, and then you can implant your implant. Like, so this was a very helpful technology, and still it does. It is still a gold standard in terms of moving from mechanical based surgeries to a surgical navigation, which is also known as computer assisted surgery, or you might have seen in certain hospitals. This was very, very helpful in terms of placing the implants at a right angle orientation and maybe sizing into the body also. Then came the custom instrumentation. Now, what is the custom instrument? Again, this is instrument and not an implant. So what it did, custom instrumentation, is that you take a CT scan of a body, right? Do it in a CAD, remove the material, and so the whatever the imprint it is, subtract the from the 3D model of the patient. What the imprint is, you place it in the patient's body inside the surgery, and it places, and it provides you the guidance. So all the pins you see, red, blue, it provides the guidance for the implants to be placed at a right angular position. Again, this was also very helpful technology, but it didn't lasted much longer, or it still is in a very nascent stage. It is there, but it didn't lasted longer because there was one thing that you need to do a CT scan for sure. And there were certain accuracy challenges in terms of placement because you need to have an exact match. So suppose your instrument you are fixing on the bone, it can, if it places in two places, then you are off, okay, which is the right location for it, and then you can pin it and put the manual instrumentation. So it was not giving a complete, solution, but it was a partial solution for the patients or the surgeons. Again, the challenge in this, you have to provide the sterile instrument every time inside the surgery. You need to acquire the CT scan of a patient, put it in the timely surgical time. You have to supply this guide. So this was a novel technology, but it didn't last it long uh, in the orthopedic segment. And now this thing is the latest, and the latest is a surgical robot or the robotics technology or surgical robot or orthopedics robotic surgery. So again, robotics are two types when it comes to surgical robot. One is the hard tissue, one is the soft tissue. So soft tissues are mostly like heart surgeries, bariatric surgeries, endoscopic surgeries. Hard tissue are the ones which are done in orthopedics. Both are different. So anyone says, if you see Da Vinci robots and everything, those are soft tissue robots. The one which you see of Stryker, Zimmer, or even Merrill, those are hard tissue robots, which is used for the bone. Again, both are different technologies. So just don't get confused when you see these things outside in advertisement. Now, surgical robot, I would say, is combination of surgical navigation and some part of custom instrumentations. Surgical navigation, it's an advancement of surgical navigation because you have the navigation part still built inside the robot. So navigation is still being used, but the execution is done with the help of CT scan, which is done in custom instrumentation. So you import your CT scan, feed it inside the navigation, right? Do the pre-planning, and then while executing, the robot does the execution inside the OT with the help of surgeon. Obviously, surgeon is still in the driver's seat, but the surgeon does the cut or the placing of the implants while doing the surgical robot. So I would say it's a very much higher advancement of surgical navigation. So where it provides the guidance, it provides the information based on the patient implants, but it does the further step of cutting and placing the implants inside the patient's body with a higher accuracy as achieved in the surgical navigation. So it's removing some biasness or some inaccuracies which surgeon might be having while cutting it because of the steadiness, whereas here the steadiness of robot is more accurate, considered accurate, I would say, as of now. Any questions?
Any question, participants? So there is one more question. What future opportunities do you see in the production to reduce medical cost and enhance the patient treatment outcomes?
See, the cost. See, the cost of manufacturing, honestly, is not much. Right? If I'll just say, right, the implants which you put inside the body, let's say just an example of the knee implant which you are putting it right now. As per government mandated, I think it's 50 or 60, 70,000, which is the cost of implants which you can claim right now, which is equivalent to earlier the cost of a bike. So a bike used to have handles, seats, engine, everything, whereas the cost of implant is just a metallic three component. Still it was high. So it's not the cost of implant, but the volume is not that much of as your bike, and the R&D cost and regulatory cost is much higher in cases of implant. So the manufacturing cost is not much higher, but the cost to do trials, clinical trials, let's say to an extent, the R&D development cost, it takes 3 years minimum to develop any implant system. Minimum 3 years, I would say. If it's a novel device, it can go to 5 years also. So you imagine the amount of effort required to develop this implants is really high, and ultimately everything gets cost built into the final product. But yes, with respect to 3D printing and certain mass manufacturing process, you can still achieve the lower cost, but it will not go beyond a certain lower cost, I would say. Imagine, I mean, it's the cost of surgery is also to an extent, like imagine, like surgeon, it's not the cost of surgery, right? The implant is one piece of it. You have patients, so you have, sorry, nurses, you have all the equipments, the consumables which are there inside the surgery. So I would say that in India, the cost of surgery or cost of implants is the lowest in the world. You go doing same surgery in US, I can easily say it's almost 10 times the cost in India. So I would say we are fortunate enough that we are getting this at such a lower cost. Okay.
Okay, thank you.
So now let me come to standard implants, right? So now we are talking about a custom implants and standard implants, right? So standard implants, I just compare it with the chart of your shirts, t-shirts, or even trousers, right? So you have small, medium, large, extra large, double XL or triple XL, right? These are standard. So no matter whatever you are, you have to fit yourself into one of this device. That's a standard, because that's how it has been prescribed, or through there's some R&D into it. Okay, this is length, this chest and this shoulder needs to be there for any standard. So obviously it covers 70, 80, sometimes 90% of the people, but then it doesn't cover people like this, right? When you go to buy a shirt or a t-shirt, right? Similarly, the implants are also there where you see small, medium, large, extra large. Here also you can say size 1, 2, 3, 4, 5, 6, 7, 8, which is an overall anterior posterior height, medial lateral width. These are the standard way of representing or measurement. Similarly, what you have length, chest height, shoulder length, sleeve open and sleeve length. This is similar, which exists in case of standard implants also, which is available. So if you go inside the surgery, if any one of your colleagues or even your parents or anyone goes inside the surgery, surgeons try to fit in standard implant onto your body because of a lower cost. Your availability of these implants are much higher, right? You go to any store, you will get all these standard small, medium, large, extra large in quantities. Similarly, these implants are also available in quantities at the surgeon's disposal to place it inside the body, right? So your surgery becomes faster. Like you buy the shirt, it becomes faster. Similarly, his case is the faster here. So surgeon tries to fit your requirement within the standard sizes of implants. But there are cases where your bones is completely, you can say, chewed up or degenerated or removed, right? Or your knees are, let's say, this fused. So there is nothing left. It's so fused that ultimately you have to cut it in a very different way. And your standard implant will not fit into those positions, right? So just to create correlation, it's not, it is maybe suitable for 70, 80, 90%, depending on the type of what you're buying. But there are cases where this doesn't fit or this cannot be fit because of inherent deformity, inherent condition of individual patient. Every patient is different, but the conditions can be different and you need to have a custom implant required in these cases. So the custom implants, that's how the custom implants are built so that you can, it fits the right patients and you can gain the mobility and it removes the pain. Ultimately, these are the two primary objective of doing it. But then the standard cannot be fitted in, and that's when you go to a custom. And similarly, the standard shirt cannot be fitted in this kind of patients, and you need to go for a custom or tailor-made. So that's the philosophy of standard implants versus the custom implants. Any questions? We can take it or I'll move forward. I know it's a little simple, but just wanted to create an analogy between the shirt and how we do in the implants.
There's one question. How much time it will take to customize a new implant if suppose doctor needs immediately? So how much time it will take to making a customized implant?
I would say minimum 1 month. It can go to 2 months, 3 months also. I'll again go through the process in the next slides. Why it takes so much time, I'll just tell you on that. But it takes minimum 1 month. It can go to 3, 4 months, 6 months also. Depends on the conditions of the patients. But there is a definite set process, and that's why it takes more time. I'll just go through the process in the next slide, so you will at least know what are the steps to do a custom implants. But it takes minimum 4, maximum it can go to any number of months, at least 6 months. Minimum 1 month I have seen, not before that for sure. So why custom implants, right? Standard fit size doesn't fit all patients. Every deformity is different and require different approach. Technology advancement is also one of the, because the custom implants earlier used to be, traditionally manufactured. It used to take too much time. And that's why certain surgeons used to go to the standard implants, then the custom implants, because if it takes too much time and patient is not ready to wait, you need to fit in your standard implants. But because of the custom implants, there is a faster, meeting the need of the patient, and that's why there is a much more uptick in the custom implants. And obviously, it provides personalized solution. Like if you see off the rack, a picture of off the rack, a shirt, a blazer and a pant, and if you see a custom made, it really fits you nicer. Similarly, providing a personalized solution so that it meets your requirement, and ultimately it gives you more longer longevity of implants and gives you more mobility. So that's the main aim of personalized solution, and that's why the custom implants are generally adopted compared to the standard implants. But the first choice of any surgeon is to implant the standard implants. If he's not able to do it, and if he sees the need of a custom, he asks for the custom implants to be placed. And it obviously requires time, effort, money, and everything. Again, 3D printing of material and variations. So I'll not go deeper into it, but then these are general available material technologies, FDM, SLS, and SLA. Again, these were mostly used for plastics material, FDM, like fused deposition method, SLS, and SLA. Cost varies. FDM is much cheaper, but then the accuracy and everything is little challenge. SLS, which is really costly, but it gives you a functional part. It's a lower operating cost. Plus, it is autoclavable, certified medical grade material. So at least you can autoclave it. So any instrument or anything you take inside the surgery needs to be sterilized, and this provides a material or technology where you can, ultimately autoclave it. The third is the SLA. Again, it is autoclavable and it also has the best quality and smaller parts. Again, it's a lower capex, but it gives the right approach in terms of materials. Again, this 3D printing technology has been existing, but then it is mainly limited to plastics, right? Again, plastics, we cannot use it except certain cases where we go with a metal implant, a metal, right? So this is a FDM, where the companies have FDM machines, fused deposition method. Stratasys is the major in this, Flash Forge and Ultimate Maker. So it's basically you are putting the material fused or layer by layer on the flat surface and building the part from top to bottom. This is an SLS process where you have a part and then you create the melting of it within the part, and once you remove the powder, ultimately it gives you the whole part in terms of manufacturing process. Again, the company is EOS and 3D Systems. You see this is removing the powder, and ultimately it creates the part out of the fused material. Then again, there is an SLA, which inside the liquid, it creates the electric beam, and which ultimately melts the part, and then it gives you the 3D printed part. Formlabs, 3D Frozen are some of the technologies. This one is the predominantly being used in orthopedics, which is because this is kind of near or new thing where you are doing a 3D printing of metal parts. It was mostly used in aerospace since some time, but it has come to the medical devices. Again, the challenge, aerospace, you don't have too many parts to manufacture. In medical devices, definitely the volume is huge. So I can tell you, we have a manufacturing unit in Ireland which does the 3D printing, and we use these companies, to buy the machines and have our proprietary manufacturing process to do the 3D printing. We had initial one setup. Now we are running out of space every 1 or 2 years because we have to buy more and more machines to increase the volume of 3D printed parts. But Then these are like E-beam or electronic beam, which has been the major method of manufacturing these implants, is being widely used. If you see like temperature exists in 10,000 degree, 1,000 degrees Celsius, so that's how you build your part. It has been widely used, and I would say now 3D printing parts may overtake the conventional manufacturing parts which currently being done. So there is still conventional manufacturing, but 3D printing has been the forefront in certain medical devices recently because of the advantages which we discussed earlier. But it really is upping the game in terms of not only cost, but then there are reduced material and combination of manufacturing processes which you can do in one setup, and you can manufacture large batch size within one setup. This is giving advantage in terms of manufacturing 3D printed metal parts, which is used mainly in orthopedics. You can say hip, knees, spine, trauma to an extent, like mandibles and your skull implants are also being manufactured now in this. Any questions?
I think there's no question. Please continue, sir.
Okay. So again, the question on custom implant development process, right? These are kind of steps which are done in the custom implants. You know, let's say when a patient goes and surgeon decides that this patient needs to do a custom implants, that's when the process starts. The first process is CT or an MRI scan. CT scan is required because you need to take the bone anatomy, devise your custom implants based on the deformation which is there inside the implant. So this is kind of a first step. Second step is segmentation, right? So the images which comes to you are kind of an X-rays layer by layer. You need to create a 3D model out of the CT scan in order to design your custom implants. So that's a segmentation. Surgical planning. This is a really important step because this segmentation is done by an engineer, right? Who sits in the computer or does through the CAD work, he designs on certain implants, but he's not a clinician. He has to send that design to a surgeon, whether I am doing my implant correctly, whether the position is right, whether the approach is right, whether you will be able to approach and fix this implant into the patient's body based on my planning. Surgeons do change the implant's geometry, implant's positioning, sometimes sizes also, and ask the engineer, no, I want my design to be differently than what you designed. And then based on his feedback, engineer designs the custom implants. So that's why it takes a little longer, right? So it's not just the segmentation, then the surgical planning, and then the 3D printing of the implants. And then post the 3D printing, you need to do sterilization as well, packing as well, which has to be, cleaning as well, and then shipment, and then inside the surgery. So these are technically higher level 5 steps which happens to develop any custom implants. Again, if you have any questions, you can ask in between also, but I'll just go through the steps. So CD scans and 3D visualization, right? So CT scans are, if you see on the right side, these are the images of CT scan, right? These are the basically the 1 millimeters of scans which you move up, and these are the lines which you are seeing are the bones. So ideally it's 1 mm or less, which is more feasible if you want to do or accurately manufacture custom implants. Because if you do like 5 mm or 10 mm or 2 mm, you get a waviness in terms of your implant and you will not get a continuous curvature. So 1 millimeter is generally considered ideal to design your implants. And this is the first steps in terms of utilizing the CT scans. MRI generally don't prefer. Reason being, MRI is more soft tissue. You don't get accurate information of bone. CT scan is more on bone and bone density and quality. Again, the implants are fixed or replace the dirty bone, or I would say the diseased bone, and fixing of your custom implant. So if the bone geometry is most important, and that's why the gold standard is always a CT scan and not the MRI. Again, some surgeons do MRI also just to see the ligaments and the tendons and the placement inside the CT scan. But to design the custom implants, you 90-95% you require CT scans always. Segmentation, right? So this segmentation is basically, let's say you have one layer of let's say you have an X-ray, right? You draw the outline in that X-ray. Now you take 1 millimeter away from that X-ray placement, and you do the outline. So you basically draw one layer and make that layer into a 3D bone. That's what is known as segmentation. So segmentation is basically you are segmenting the CT scan information through a layer, build that layer one by one, and that's what constructs your 3D bone model. Again, segmentation, and there is a concept of 3D CT where you can get directly a CT image in terms of 3D, but it's not accurate enough. And that's why still the manual segmentation is really important, to create a 3D bone where you can design an implant. With 3D CD, you cannot design an implant because of the inaccuracies which is there in the 3D CD. Again, the time consuming. So imagine you get your CT scan. I'm just giving you a ballpark number. So 3D CT scan is done at a patient. Surgeon reviews it and sends to a company or manufacturer or people who design the CT segmentation, right? So it takes generally 3 to 4 days. If it's going on a CD, it takes 2 days sometimes to upload and see the accuracy of the CT scan. If sometimes it's not accurate, people might require to do another CT, but generally it's not a problem. So it takes 2 to 3 days just to transfer the CT from a CT scan center to the company who's going to design. Segmentation depends on the criticality or the placement, but segmentation generally takes 3 days to 4 days, depends on the type of bone and the deformity inside. If you see the bone quality, right, you see this is the actual raw segmented bone. You see the bone quality. There is nothing left in the bone. There's a fragments of bone everywhere. If you see the left side and the right side, left side is completely healthy. The right side is the bone quality which you get in the patient. So imagine you have to do a surgery. When you open it up, this comes as the fragments. Everything is just falling apart, and that's where the surgeons start to operate. So imagine the complexity, what is there inside the bone. And this is the basically a segmentation process. One second, I think this is a little heavy in terms of files, so it has hung up. I'll just open it up again. Yep. So then this is the basically a segmentation process which I was telling you about. So this is kind of typical. Again, the preview is of my segmenter, which is made in India software. Again, you can contact or you can Google it. It's done by an Indian is a very close friend of mine who did develop this software. There's also a software which is kind of considered gold standard, which is Mimics, which is available in global environment, but it is very costly. So this guy basically designs and sells the software as well as provides a custom implant. So the view you see here is of a semi-segmental screen where you have the CT scans you see on the all the three views, and that's how you continuously develop the bone model, which you see at the right-hand corner, uh, which is a segmentation process. Yeah, you see this is the segmentation process again. You develop the whole bone model out of it. And again, it's a little bit of I would say, art, because you have to find out, differentiate between a good bone, an osteophyte, or a ligament, or sometimes the anomalies which are there in and around it. So you have to accurately draw it, identify the bone quality, because there are a lot many informations available in the CT scan. So once you start doing segmentation, you can in fact know the bone quality, sometimes bone density also you can evaluate, and tell to the surgeon that, okay, if you're fixing the bone implant here, if you're putting the screws here, it might not be a good idea, because the screws may be put it into a wrong location where it will not fix it permanently. It will start wobbling once the patient starts walking. So it provides a lot of information while segmenting. So the engineer who does it really needs to understand the anatomy, really needs to understand the bone quality, and work with surgeon basically to create an implant which can be fixed and which ultimately helps the patient. So it's segmentation is a process, but then ultimately there are information which you get in this as well. Again, this is obviously done pre-surgery, right? You can see the process, how they do it. So this is kind of an implant already there earlier, and they're kind of removing it, remove the material. It shows how is the material right now in terms of bone, how much it is left. If you remove the existing implant because of other conditions, it shows the overall 3D view of, again, the visualization is important because surgeon sees in terms of CT scan, but when you uh, make a 3D model, you can do a measurement, you can do a rotation of it and see where my bone is, where my real estate is in terms of placing the screws, the implants, where I can fix it. So visualization is one of the piece based on which because surgeon, if you give them the implant, they will not know what should I do, like where it is fixing. But with help of visualization, you can accurately know how my implant will look like, where my implant will get fixed into the bone, where should I put my screws for fixation, and do I need to be aware about anything which I cannot see in a physical patient, which is really bad um, inside the OT. If you open the wound and if you see some, you don't want surprises. So with all the information you get pre-surgery, this becomes really helpful tool. So again, as I tell that surgical planning, so you imagine, so this is a cup. So basically, let's say it's a hip joint, it's an acetabulum of your hip. You place your cup. Now you can easily design what it should be your diameter, what should be the inner diameter, what should be the axis. You can everything define. Again, this is all happening pre-surgery. So you don't design, you don't open and start designing. This is everything happening pre-surgery, every planning segment based on your segmentation 3D bond model. You can do the surgical planning, what axis I want, what placement I want, what size it will be, if I want lower size, if I want higher size, if I want more flanges so that it can fix to the correct amount of bone. Do I need how many screws? Do I need 4 screws, 2 screws, 1 screw, or do I need K-wire basically to fix this implants, right? So every information is available to a surgeon where they can easily plan the surgery so that there are no surprises and he can get in and get out by putting the implants perfectly inside the bone. Any questions till now, sir?
There's one question. Is asking what are the primary advantages of the custom implants over standard implants in terms of patient outcomes, such as fit, comfort, and recovery time?
So I would say the custom implants is mostly done for a very specific condition, right? If your bone quality like this is like this, right, then you cannot place your standard implant in. If you place the standard implant, there is a high chances of you going to a second surgery within 1 or 2 years. So imagine a person who has gone through the surgery, did the rehabilitation, or you can say physiotherapy for 2 months, 3 months, going through the whole pain of surgery, and after 1.5, 2 years, you have to go again for a surgery, and you have to put a higher construct implant again, a different kind of implant. Most of the patient don't go itself in the second surgery; they live by it with it, and again they are in the same condition before placing the implant. They cannot walk, and there is a pain. With custom implants and going through this, they can directly fix the right size of an implant, right placement of an implant, and right design of an implant. And it prevents you from going through the pain of revision surgery or going through the surgery again. This is one of the main advantage. And again, standard implants are not available in certain cases. Let me tell you an example of tumor cases, right? Where you have a tumor inside your hip or a knee joint or a spine joint, where you have to remove the tumor by removing certain bone, and there is no standard implant available to fix those kind of problems. So in those cases, definitely there's 100% chance that you have to go for custom implant. There is no other possibility. The third case can be a revision cases also, where standard implants are there, but then those implants have failed because of infection or many other reasons. Like infection, it gets spreaded to inside your bone. You have to remove those bones and place custom implants, because the real estate or the supporting structure, which was for standard implant, has gone, and now you have to place the custom implants. So these are the certain scenarios where the custom implants are really helpful than the standard implant. But again, I would say custom implants is a time-taking, costly affair. That's why people don't go for standard implant, don't go for custom implants, and standard implants are much easier and everything to do. But where it's needed, there is a need for custom implants. If you have your genetic abnormality, standard implant cannot be fixed. So all those cases are for the custom implants in general.
Hello, sir.
Yeah.
Hello, sir.
Yes, yes.
When we deal with any implants, there are the two aspects. First one is the mechanical strength, and the second one is the biological parameters. So in case of the bone implants, we generally deal with the mechanical their strength. But apart from this, the biological is also a very important, play a important role. So how you can decide the porosity of that materials or that designs?
So again, correct me if I'm wrong. So you are saying the one is the definitely structural part, which is a bone, right? The other biological
Yes.
is in terms of your the components of your blood and everything else you're saying?
Because when we are dealing with the any implants, we have to maintain the biological part also. So because I have already worked on that in acetabular, so we have to design a TPMS based structures. So it will be the play by or done by the porosities, that is the different
Right.
aspect or different ratio, 60%, 70%. So how you can manage it?
So in terms of so porosity is ultimately helping you in what, right? So when you give a porous surface on the backside, which is fixing to the bone, what it is giving you? Why you are doing porous structure?
Because it's support the biological phenomena.
Yes, so it basically not supports, I would say, it basically helps you in fixation. So it basically
Yes,
fixes on the existing bone.
yes,
And then
yes.
there is a bone ingrowth, right? Which happens over the time, over the years into the bone. So that's where your porosity or the porous surface basically helps. Now, while designing it in terms of customs, you need to fix it. You need to have a porosity in terms of providing porosity in right areas, right? If your bone, again, those informations you will get in terms of your segmentation itself, that how porous is your bone, whether you're a cortical bone or whether you're cancellous bone, or what is the quality of your cancellous bone, and if there are chances of bone ingrowth in those regions or not. Um, if there are chances, then definitely you provide structure or porous structure in those areas. But if then there are not, then you don't really give those kind of porous structures in those areas. So ultimately, it's identification of those areas within the segmentation process. Consulting with surgeon is really important, because until another surgeon feels comfortable, you should not do it. Again, I'll give you a caution on the downside of giving porosity as well, right? So if you have porosity and if the bone ingrowth happens in that, tomorrow, if you have to go to the revision surgery, you have to completely remove that bone, because bone has grown inside that implants, and you have to basically chop off that complete area to remove out that implant systems as well, right? So there is a downside of porosity, but on the majority of an upside, porosity needs to be an area where the bone ingrowth can happen. Otherwise, there is no use of it, and you waste much time and energy, because creating a porous structure is really difficult. It's not that easy.
And sir, apart from this, you have to take, because when we are putting the implant on the body will be suffer from the stress shield in the fat.
Uh,
So
so
what your
definitely.
company will be the consider, or which types of steps you have to consider while designing this or removing this phenomena?
So stress yielding definitely is there an effect, because again, see how why the stress yielding will take an effect, right? When you place this, you have to fix this implant into it, into the bone conditions, right? What are the methods? One is the tight fixation, which is generally in this kind of conditions you will not. You fix it
Yes.
through mostly K wires or bone screws, right? Bone screws is the ideal method. But then bone screws, availability of bone screws at an angle with the right length and a right projectile is also very difficult if you do it in the standard. In custom, with the information of CT scan and segmentation, you can devise your bone screw, which area, which angle, because I've seen most in standard surgery, some people have designed screws which goes in one direction, but then it can ultimately come out in, and it may go into your certain arteries, or sometimes both two screws interact, or it may interact with any existing implants or the plates which is already there. So the fixation of this implant is the key, because this implant, custom implants by itself are not fixed because of the inherent geometry or the real estate available for them to get fixed. So it's mostly the screws placement and type of bone where you're placing that screw is really, really important.
Sir, thank you.
Yep. Yeah, again, this is the preoperative planning. So this is ultimately what surgeon gets in general. Okay, this is your bone. This is the implant I'm designing. You see in golden color. What is my medial size thickness? What is my lateral size thickness? What is my angle? 6 degree with anatomical view, 0 degree with TA and PCA, postcondylar axis or transepicondylar axis, how it fits. So this is kind of an image which a surgeon gets to decide, okay, whether whether the implant which I'm seeing is perfectly fine. Do I need to move up? Do I need to move left? Do I need to move right? Do I need to change the angle? So this kind of an information, a surgeon replies by saying, no, I don't want 0 degree, I want 3 degree, make it 3 degree. Then the engineer does design the implants based on 3 degree, again goes to the surgeon, and he approves it. Remember, like any medicine, this is also a clinical decision which has to be taken by a clinician only. And it is always a right for a surgeon to decide the implant's positioning, sizing, orientation, so that he can have a best outcome, because engineer can design based on the information available, but he's not going to be there inside the surgery. He's not going to execute inside the surgery, and he's not going to face the patient. So it's ultimately surgeon. It's a surgeon and surgeon who decides the custom implants, its geometry, its angle, its orientation, everything here. So this is the most important aspect of pre-planning, or I would say surgical planning, which has to be done by a surgeon in consultation with an engineer. So technically, it's an engineer who works with the surgeon, or a biomedical engineer who works with the surgeon, and together they design, and the surgeon decides, okay, this is my perfect way of getting my custom implants. With standard implants, you don't get this flexibility. You don't get the flexibility. I want to make it narrower. I want to make it broader. You don't get that flexibility in standard. Standard is what is available. You make it, cut it, you adjust it. You can do it. If not, go to the custom. So that's the beauty of the custom implants. So again, as I said, like this is for purely complex cases. Like if you see preoperatively, you see this is the bone. There's nothing left in the bone. And this is kind of an implant you basically design in and around where there is a sufficient real estate available, how many screws you will place, how many provision of screws you will give, what type of screws, what angle of screws, because at a one wrong angle and it can go inside your femoral artery and a patient can go into paralysis there and there in the surgery. So it's really important. Whosoever is designing, he has to see all those aspect, what angle the screws needs to go, what should be the diameter, inside diameter, outside diameter. And again, this is an example of hip. Similarly, is case for a knee. Similarly, is case for a spine. Similarly, is case for any trauma cases which you are available on mandibles or inside the skull. So the next step is 3D printing. So again, this is kind of an optional step, but it's generally done nowadays. What you do is you do your 3D printing of your segmented bone. You do a 3D printing of your implant. These are in plastics. You send it to a surgeon. He sees it in physical form inside his OT or his, you can say, OPD, and decides whether it's a right implant or not. And this is another extra chance for him to review it, or you can use it inside the surgery also sometimes to see really where he can place it or not. But this is again a 3D printing of plastics, which is very low cost, but it helps in surgeon in planning it better, or a last chance before you manufacture the implant in metal. So this is kind of a 3D printed technology being used for just for plastic, just for visualization and actually seeing in hands. And again, 3D scans and visualization is something which you see on actual implant, which gets manufactured. This is again a 3D printed. The implant geometry, which you basically fix it on the bone. So you see the complex geometry of the implant which gets manufactured. Any questions till now? Again, I know I covered a little faster, but I just wanted to make it continuity so that you understand the process, but we can definitely take any questions within that. Any questions? Yeah. No questions?
No questions.
Okay. Because I don't have much, but I'll just go ultimately last in terms of benefits of custom 3D printed implants, right? It is because of possible to manufacture difficult contour implants. Earlier, standard implants are fixed standard contour. In 3D printed, you can get this kind of contours also, which ultimately matches the patient's anatomy. That's what you want to ultimately achieve certain results. And that's why it is really beneficial in terms of manufacturing or doing a 3D printed implants. More patient specific than manufactured through conventional process. Conventional process, you will get more or less this type of shapes, but in 3D printed, you can get this type of shapes also, so that it really helps in matching the contour rather than fixing a shirt on yourself. Here, your shirt is basically fitting on you perfectly so that you look nice. Similarly, in the case is in 3D printed, it ultimately designs the implant so that it fixes on your anatomy perfectly, and it helps you achieve the larger goal, which is mobility and reducing pain. Does not require additional manufacturing process such as HA coating or mesh creation, because like earlier we discussed, the porous surface you can easily create with 3D printed, and it produces really nice porous structure where you can have a bone ingrowth, and you don't need to do an HA coating or mesh creation, which is an additional process. And sometimes there is a challenge in terms of coating, HA coating. There's a sticking of it, which can happen, which can get removed over the time, whereas this is inbuilt inside the metal component, so you don't need additional manufacturing process. So you're basically saving certain cost in manufacturing with respect to 3D printed. It is cost effective to manufacture. Now, why I'm saying cost effective is to manufacture this small of an implant, you need to take complete block. And then you need to do machining, remove out the material, basically a subtractive process, and then manufacture. Still, you cannot go inside and make the contour. Here, it is very cost effective because the amount of material used is probably 20% of the whole material which is used in conventional manufacturing. So imagine the amount of material which is saved by moving into a 3D printed compared to a conventional manufacturing process. It's a huge in terms of lightweight, because you can manufacture different contours, which is not required. Because of conventional 3D printing process, you need to have a tool, you need to have an access to the tool, whereas in here, you can create a hollow structure, you can create a porous structure, which is light in weight, and ultimately helps in mobility. Very quick manufacturing, essential for custom devices. So imagine like this kind of a contour to be manufactured, it will take much more time and much more post-processing to manufacture this kind of an implant. Whereas in 3D printing, you can probably do it in 1 or 2 days itself. It's very, very, very quick compared to the conventional. So that's why I would say the manufacturing time for the custom implants has reduced drastically because of 3D printing itself. Earlier, it used to take 2 weeks to 3 weeks minimum. Now, with post-processing and everything, you can do it within a week. Manufacturing, cleaning, certain kind of deburring, or you can say final polishing also. So that's why the manufacturing time has gone down drastically. And again, the last one is environmental friendly because you don't use many hazardous chemicals, which is used in manufacturing the conventional processes. You're reducing very, very less, you can say, material, and ultimately hardly there is a wastage of 5% of material. In conventional, it's around 60-65% of material gets wasted. So it's really environmental friendly in terms of non-usage of hazardous material, reduction in terms of number of amount of material being used to manufacture the implants also. So that's all I have. Again, to let you know, I've covered, just to recap, I covered what is the orthopedics in terms of implantation, what is the role of custom implants compared to standard implants, what is the use of technology, how the technology has evolved in terms of manufacturing and in terms of placing the implants, and then the process of doing a custom implants and 3D printing. The last and not the least, I'll give you a quick glimpse of what is the use of robotics, let's say, on placing of this, right? So there are projects or thoughts which is already going on in the market, so where you can place a custom kind of an implant with the help of robotics. Earlier, because of conventional, you have to make a definite cut, but because of robotics, you can make the fine cuts, reduce the removal of bone, and place the custom implants correctly, because you are doing the fine removal of bone at the right place with the help of burrs through a robotic and placing the custom implant. So ultimately, it's a really customized surgery, so that your implant is based off your CT scan, your bone removal or surgery is done because based on your CT scan and based on your implant, and ultimately you get a right fixation at a right amount of metal and a right orientation. So if you marry 3D printed 3D printing implants with the robotics, it can achieve a real good outcome for patient because it's a really true customization based on patient then. Because in conventional, you will place the implant, but then it might be an orientation a challenge. But with the robotics, you can get a perfect outcome married with the custom implants or custom 3D printed implants, let's say. So that's all I had. I'm not sure if it's long or short, but this is the
Question,
practical
sir.
applications which
One
we have
question,
used.
which has got a good product life cycle, sir? Custom based or standard ones?
Sorry, come again.
Which has got good product life cycle? Custom based or standard ones?
Product life cycle in the sense longevity of these implants.
Yes, sir. Yes, sir. The lifespan.
Um, both are good. I mean, see, any implants you decide which passes through the regulations, right? Mostly it it is tested or designed for 10 years of our lives, right? Standard implants is definitely tested much a higher degree because there's a fixed geometry and you test it based on your design. Custom implants, there are certain assumptions you do that it will last this much of a device because you cannot test it, right? Because it's
Correct.
just one implant manufacturer, you cannot test
Yes,
it.
yes, sir.
But because of um, the geometry and how it is well fixed into it. Again, considering the complexity of the surgery, same. Custom implants will last longer because there you have technically you have fixed the implant, which may be 70-80% correct only. Whereas here it is more or less 95 to 98% correct. 100% no one can assure, but 95 to 98% correct. So that's why the longevity of custom implants may be good, considering that the bone quality or the deformity is same between those two.
Mm-hmm.
It's really customized, right? So you can imagine there is less stresses on the bone because your deformity is really high, and that's how it is being designed. So the stresses which you encounter is really good. The only downside is it takes time, right? 2 months, 3 months. You have to really be patient. Again, you see the steps. Most of the patients don't know the steps and don't know the difficulty or the process which goes behind designing it and manufacturing it. But the cost and the lead time is really little higher because it's really customized. Like nowadays, you go a tailored shirt is still costing more than the ready-made shirt, right? Ready-made shirt because of the lower cost.
And sometimes that lasts for a longer time also.
Yes,
Tailored ones, yeah.
because your stitching is done by a tailor, right? There it is done in masses, right? Here the tailor is fitting you exactly, and stitching is done as per the by an expert thing, whereas that is done in masses in manufactured setting, right?
Can you say that, sir, the standard ones, for the standard ones, we cannot go for this, all the six principles of motion economy, whereas for the customized one, we can go for more number of degrees of freedom and more number of principles of motion economy can be applicable there.
No, so see, standard implants are also good implants. Like they are done for the masses, right? And
Yes.
they are also designed based on so standard also. Let's say standard, you are saying 6 degrees of freedom and all, right?
Yes,
So
sir.
there are standards also, standard implants also. You have various categories. One is let's say partial. One is the primary surgery. One is the revision surgery. One is the oncology surgery also. There also you have standard implants available.
Oh, great.
And definitely it fits good. There can be again the beauty with the body is that it is very forgiving. 2 or 3 degree or sometimes 4 degree of variation, your body adopts, right? Because more body adopts to any foreign thing and tries to adopt it and try to work through it. So body really adapts to standard implants really well. It's cheaper,
Mm-hmm.
it's quicker. Custom implants is something where you cannot fit your standard. It's really difficult, and the outcome you will get will not be good, and you will know that you will the chance of failing of standard implant in this case is really high. That's where custom implants helps you in achieving your degrees of freedom with degrees of motions as well.
Yes, sir.
Right.
Perfect. Yes, sir. Thank you, sir. Thank you so much. It was really insightful, sir. Yes.
Yeah. Thank you. And again, this is all my practical experience. So I don't have, research-based thing, but this is what we do. This is what, we have learned, and this is what we execute. And the journey of evolution is really interesting. If you ask the surgeons earlier, now with robotic surgery and with advancement of AI and everything, you will see a drastic increase in use of custom implants with the help of robotics to place it in. Again, the time duration which was there to manufacture to provide a custom implants is getting reduced because of 3D printing. You imagine the next level of 3D printer available at surgeon's office, right, or outside the OT. Engineer designs it outside, right, somewhere sitting in the office. So once the surgeon approves, he just gives the print command. The 3D printing happens right at the hospital. He can take out the implant, do some post-processing, and use it there inside the OT. So that's like a definite level, but it requires, computation power, the infrastructure at a hospital, and the robotics kind of technology to really do it. But that would be next upcoming stage where you have a robot which does the programming on it, does the pre-planning, surgeons approves it, gets 3D printed, does an implant, let's say within a week or two at maximum. That would be a thing where you will see people shifting from standard to custom more, but it's a time to come.
Yes, sir. Perfect, sir. Thank you, sir. Thank you so much, sir. Thank
All
you.
right.
Another question, participants?
Right.
I think there's no question, sir. I have one question. Suppose a student want to apply in his tiger and they want to pursue in this particular field. What skill sets he also should have?
So there are a couple of So definitely he needs to have a medical or bio. There are two streams now, right? If you see in this, one is the mechanical engineering to an extent on design side. When you do a custom, there is a biomedical engineering also required because to understand the bone and mechanical engineer don't study the bone and the anatomy. Biomedical student does, right? So it's more the knowledge of anatomy, the knowledge of how biomedical impacts your implant design. Little bit of segmentation also, though it's a very definite skill which can be learned easily outside also or inside. It's not a too difficult a thing, but to do a segmentation and to know the intricacies of the bone and the bone quality is also really important. Um, I think those are the basic skills. 3D printing is something which is done by the manufacturing. Again, you need to know the basics of 3D printing and limitations of 3D printing also, right? Sometimes you cannot do certain things with 3D printing because it's built from bottoms up, right? There are certain support structures which you need to build the implant also. So I would say it's a basic engineering, but pure mechanical engineer may not be able to do. A biomedical engineer is an ideal, but with certain mechanical background in masters would really help. Like bachelor's, let's say if is done in mechanical and masters in biomedical, that's kind of an ideal thing. But again, biomedical covers various gamuts of orthopedics. So it's a basic design, I would say, knowledge of anatomy and 3D printing. I think these three skills are important. Again, certain skills we teach it right.
I think there is no question from the participants.
Yeah.
And thank you so much, sir, for your insightful session on this 3D printing and custom implants. I think the participants must have gained the valuable insight, and they will inspire with your talk, and hopefully if they want to excel in this field, so they will follow your instructions.
Sure,
Thank you
sure.
very much.
Thank
I
you.
truly appreciate your time and contribution.
No
Thank
problem.
you.
Thank you. And you can reach out to me if you need any information further also. No problem.
Sure, sure. Okay, we are running BTech in biomedical engineering basically, and mechanical
Okay.
engineering too.
Sure, sure.
And we want that our students can apply your companies, and may they get some idea, at least they get some internship too. So
Sure.
at least they will see what the industry doing. So because we will able to reduce the gap between the academia and industry.
Yes, yes, definitely. I mean, yeah, it's more from research to this is little different, right? What do you do in practical application?
Right.
But yeah, it's a good field, upcoming field, and many Indian companies are also coming into it, right? So it's really an advancement, and you will see this, I mean, accelerating leaps and bounds in coming years for sure in India. Right.
Thank you once again, sir.
Thank you. Thank you, everyone.
Participants, you are requested to fill all the feedback form, which is already shared in the chat box. And we will join tomorrow from 2:30.
Sure.
2:30.
Thank you.
From 2 p.m. So tomorrow we will have 3 sessions from 2 to 3:30 and 3:30 to 5 and 5:30 to 6:30. Thank you, sir.
Thank you. Thank you. Bye-bye.